Good morning, everyone. Today, I'll start about the decimation in time algorithm. You remember in the last class, we have discussed about the fast Fourier transform, the radix 2 algorithm, and the different forms or the different types of FFT. That is, there are two types basically. One is the decimation in time. The other one is decimation in frequency. Clear? So now I'm sharing my screen for all of you. Just wait. Okay. So you see, it's written decimation in time algorithm. Now, what is a decimation in time algorithm? Last class I've already explained. Again, I'm telling you. You see, decimation in time, it is done in time domain. Okay, it is done in time domain, and the index n is associated with time, and the index n is associated with time. In decimation in time, first you listen, then you look at the note, because right now when I'll be telling about the note that I'm explaining, then I'll be telling it beforehand that I'm explaining the note. So first listen, then see. You see, decimation basically what is? Decimation is the process of breaking down something into its constituent parts. Decimation is the process of breaking down something into its constituent parts. Now, decimation in time involves breaking down a signal in the time domain into smaller signals, each of which is easier to handle. Like if there is a big signal in time domain, so it will be difficult to handle, isn't it? So some smaller signals, if I break it into, then those individual small signals will be easier for us to handle. So decimation in time means breaking down a signal in time domain into certain smaller signals, each of which small signal will be easier for us to handle. Now, listen, the decimation in time and radix 2 fast Fourier transform recursively partitions a DFT into half-length DFTs. Means what? Means if there is a n point data sequence like I have written, you see the note now. See the note. Let us consider a n point data sequence xn, which is decimated into two n by 2 point sequences f1n and f2n. That's why I have said that decimation in time algorithm partitions a DFT into half-length DFTs of the even indexed and odd indexed time samples. Now, this n point data sequence xn, which is decimated into two n by 2 point sequences f1n and f2n, you see, just beneath that I've written where f1n is even numbered samples and f2n is odd numbered samples. Now, if f1n is even numbered sample and f2n is odd numbered samples, then f1n can be written as x of 2n and f2n is written as x of 2n plus 1, where n is what? N is equal to 0, 1, up to n by 2 minus 1. Clear? Now, you see, so according to this, in general, what is the formula for discrete Fourier transform DFT? Xk equal to summation of n equal to 0 to n minus 1 xn into 2 factor. Clear? This one? This line. Clear, all of you? Now, you see, in terms of decimated sequences, xk equal to can be written as summation of n equal to even xn wn to the power kn plus summation of n equal to odd xn wn to the power kn. Means even numbered samples and odd numbered samples I've told you. So total xk means the total discrete Fourier transform. I've splitted it into even part and odd part. Okay. Now this even part is further written as summation of m equal to 0. I have taken a variable m. Remember, you see, this is n equal to even, n equal to odd. In the next line, I have taken this variable m. Don't think it is written wrong. It's correct. This m is correct. No problem. I've written it. I've taken a variable to denote for even numbered and odd numbered samples. Okay. So m equal to 0 to n by 2 minus 1, x of 2m wn to the power 2mk plus summation m equal to 0 to n by 2 minus 1. Limits will be same for both cases. X of 2m plus 1 into 2 real factor to the power k into 2m plus 1. Clear? This is for even, this is for odd. First expression is for even sample, second expression is for odd samples. But we know, this is a property basically, but we know wn square means wn to the power 2 is equal to w of n by 2. Okay. So here you see that for the even numbered samples, m equal to 0 to n by 2 minus 1, f1m, x of 2m can be written as f1m into wn to the power 2mk. So this I have written as wn by 2 to the power km plus, again limits are same, summation of m equal to 0 to n by 2 minus 1. X of 2m plus 1 can be written as f2m. Wn to the power k into 2m plus 1 can be written as wn by 2 to the power km. Clear? Now, this total thing, this one, this total expression can be written as f1k plus wn to the power k into f2k. If you see it, it will be written as wn to the power k into f2k, where k equal to, I have written clearly for you, where k equal to 0, 1 up to n minus 1. Clear? Now, what is this f1k and f2k? f1k and f2k kya hai? This f1k and f2k are the n by 2 point DFTs of f1m and f2m respectively. Now, you see, f1 of k plus n by 2 equal to f1k and f2 of k plus n by 2 equal to f2k. Also, wn to the power k plus n by 2 equal to minus of wn to the power k. This is a property. So, xk can be written as f1k plus wn to the power k f2k for k equal to 0, 1 dot dot up to n by 2. That means x of k plus n by 2 equal to f1k minus wn to the power k f2k. That's it. So, what we have done, we have performed decimation in time once. Again, for one individual n by 2 sequences, we can split them into two n by 4 sequences. So that I have not done. We can repeat for, I have just written it, we can repeat for further two n by 4 point sequences. Yeah. So it will be like this: V11n, F12n, V21 equal to F22n, V12n equal to F1 of 2n minus 1, V22 equal to F2 of 2n minus 1. So, where n equal to what? N equal to 0, 1, up to n by 4 minus 1. Last time it was n by 2 minus 1, now it is n by 4 minus 1. Again, so the decimation can be repeated again and again until the resulting data sequences are reduced to 1 point sequence. Means we can reduce the data point sequences to 1 point sequence using decimation in time algorithm. Now, you see, for n equal to 2 to the power mu is a Greek alphabet that I've written. The decimation can be performed mu equal to log n to the base 2 times. This much times we can perform decimation. Clear? this much time we can perform decimation. So the total number of complex multiplication is reduced to n by 2 log n to the base 2. This is the time complexity that is reduced in case of FFT. The total number of complex addition is n log n to the base 2. Clear? These all are basically short questions that can come. What is the number of complex addition? What is the number of complex total number of complex multiplications for FFT? So that time you have to write. Now, a totally new thing, but very interesting and very easy. So try to understand. Signal flow graph. You have heard this term in control system already in the previous semester. But here also it is somewhat same, but you have to know a different thing like butterfly diagram. What is this butterfly? You all know it's an animal basically. It's an insect. So about butterfly diagram, you see, let me tell you about a brief introduction of it. The FFT algorithm is shown by signal flow graph or butterfly diagram. Okay. This butterfly is a graphical method of showing multiplications and additions involving the samples. Samples को use करके several multiplications and additions दिखाता है ये butterfly. इसका graphical. So standard graph flow notation is used where each circle with entering arrows is an addition of the two values at the end of the arrows multiplied by a constant. Clear? Clear तब होगा, अभी clear उतना नहीं होगा. Clear तब होगा जब मैं be drawing a butterfly and I will be showing you. So the constant is what? Constant is basically a number which appears beside the. If there is no value, then the constant is taken as 1. Okay. अब मैं पूरा explain करूँगा clearly. You see the note now. अब अपना note देखो. क्या लिखा है मैंने? A butterfly is a portion of FFT computation that combines the results of smaller DFTs into a larger DFT or vice versa. In case of radix 2 algorithm, butterfly is simply a DFT of size 2 that takes two inputs, x0 and x1, corresponding to the output of two subtransforms and gives two outputs, y0 and y1. Okay. Now see how a butterfly looks. This is how a butterfly looks. Okay. This is how a butterfly looks. You see, the two inputs are taken on this side, x0, x1. Two outputs are taken on this side, y0, y1. And this is the arrow marks that are given. This and this x0 is related with y0, y1. x1 is also related with y0 and y1. But in the line of x1 and y1, joining x1 and y1, you see 1 minus 1 is written. Now, how to express this butterfly into equations? Given these arrows, given this diagram, now how do you express this butterfly into equations? See, since y0 and y1 are outputs, so obviously output will be the result of inputs. So I write y0 equal to x0 plus x1. Okay, x0, the straight line between x0 and y0, and the diagonal between x1 and y0. So x0 plus x1. Similarly, y1 equal to x0 minus x1. Why minus x1? Because the line joining x1 and y1 is, there is a constant minus 1 associated with it. So y0 will be x0 plus x1 and y1 will be x0 minus x1. Okay. Now each butterfly has one complex multiplication and two complex additions. One complex multiplication and two complex additions. So for n equal to 2 to the power mu, there are n by 2 butterflies per stage, and total how many, if you want to know how many stages will be there for a butterfly diagram, how do you know it? It is denoted by a formula log n to the base 2. This many stages. If you know n, you can find out how many stages the butterfly diagram will have. Now, what are stages? I'll explain. You see, in this butterfly diagram, again in the next diagram, I've considered a and b, small a and small b, as a pair of complex numbers. Now, using these, capital A and capital B are also a pair of complex numbers, so that they will be formed. They will be achieved as result at the output side. Okay. Now you see. Capital A equal to what? Small a plus Wn into b. What is Wn? Wn is our Tudel factor. And capital B will be a minus Wn into b. Why? Because this line, it is having an index minus 1. Okay? Now, one more thing. Don't think that in the previous butterfly diagram, we have not included the Tudel factor. We have to include the Tudel factor. Okay? This one just I have shown you the operation of a butterfly. But in general, always you have to add or you have to multiply the Tudel factor. Clear? So this is the basic butterfly computation for decimation in time. This is where how we calculate the butterfly diagram or how we frame the equations from a butterfly diagram. Clear? Now you see capital A and capital B. These are the outputs in this butterfly diagram, is or no? So this capital A and capital B, we need not say the input small a and small b. Means from small a and small b, when we are getting capital A and capital B, then again this capital A and capital B can be stored in the same place where small a and small b are given. Means for the next stage, this capital A and capital B will be treated as input, and again there will be one output. Yeah. Now see one example to understand better. You see what I've written. Let us consider n equal to 8. Means there are 8 samples. Clear? There are 8 samples. So first I'll be drawing a computation diagram. This is called computation diagram. This is not butterfly diagram. This is called computation diagram. And this computation shows that it is a 3-stage computation. Why 3-stage computation? You remember in the previous page, you see I've already written number of stages a butterfly diagram will have. What is the formula? What is the formula? This is the formula. This one. Log n to the base 2 stages. So here n equal to 8 in this problem that I am speaking right now. So if n equal to 8, so it will be 2 log base 2 to the power 3. So there will be 3 stages. Clear? 3 stages. So in these 3 stages, you see, I have written first, in the first stage there are 4 2-point. In the second stage there are, I have combined 2 2-points, and in the third stage I have combined the 4 points. Okay, so you see x0 x4 x1 x5 x2 x6 x3 x7. Okay, now three stage. In this three stage, you see, Why x0, x4? There are actually n equal to 8 means x0, x1, x2, x3, x4, x5, x6, x7. Clear? These 8 stages, these 8 samples, rather than, sorry, not stages, samples, I have written in this manner: x0, x4, x1, x5, x2, x6, x3, x7. Okay? Why? You see, 4-point DFTs. So x0, then x4. This is actually the way that I have written. Why I have written in this way, you have to understand there is a particular topic for this. It's called bit reversal. So that I'll be discussing later on. Okay, that will be discussing later on what is this bit reversal, why it is written in this manner. So then you'll understand. Okay, just for the time being, you see, I have combined x04, x1, x5, x2, 6, x3, 7. So individual these two has formed 2-point DFTs. Individual 1 and 5 has formed 2-point DFTs. Individual 2 and 6 has formed 2-point DFTs. Individual 3 and 7 has formed 2-point DFTs. Clear? Now, this 2-point DFTs and this 2-point DFTs total have combined this 4-point DFT combined, and this one also has combined, and these two again has combined to form the 4-point DFTs, and we have got the 8-point DFT answer: x0, x1, x2, x3, x4, x5, x6, x7. You see, notice one thing: the outputs are in serial order, but in inputs are not in serial order due to bit reversal process. What is that bit reversal process? That I'll be telling you later. Okay. Now come to the butterfly diagram. You see the butterfly diagram. Butterfly diagram. In the butterfly diagram, there are 3 stages: stage 1, stage 2, stage 3. x0, x4, x1, x5, x2, x6. The same way that I've written the computation diagram, here also I've written. And individually, I have done the butterfly. You see, for stage 1, using x0 and x4, I have done the butterfly. These are the arrows, and this is the way that arrows are given. Don't think the arrows I have given on my own. Arrows are given in this manner only. Okay, arrows are given in this manner only. Then this is the output one. Then combining this and this, I have done 2 butterflies. Combining this and this, I have done 2 butterflies. So again, I have done these arrows. Again, combining these 2 steps, I have done the stage 3. I have done the stage 3. This is the stage 3. So let me explain one by one. You see, 8-point DFTs, n equal to 8. So W8 to the power 0. Here also, not in the first step. We write the total factor in the second part of each DFT. So here, 1 butterfly. In the second part of the butterfly, I have written the total factor. Here also in the second part, I have written. Here also in the second part, I have written, and here also in the second part, I have written. Clear? And in each line, in that bottom line, I've given the index or constant -1. -1. Okay. Then it is for stage 1. For stage 2, you see, for stage 2, this point 0 has combined with 1. 4 has combined with 5. Okay. So 5 has combined with 4. Again here, 1 has combined with 0. So this way the butterfly has formed in stage 2. So here, from x1 part, I have written W8 to the power 0, obviously. And this one will be W8 to the power 2, 0 and 2. In the first stage, for each second line, there will be W8 to the power 0, dual factor. This is a way of doing a butterfly, remember. In the second stage, for the first part, there won't be anything. Now, why for these two lines I have not written the total factor? Because there are no backward paths. Okay, there are only forward paths. You see, for these two lines, there are only forward paths. But for these two lines, there are backward paths. Total factor is always written with the backward path. You see in stage 1 also, in this line, x4 line, I have written total factor. In x5 line, I have written total factor. For x4 line, there is a backward path. So that's why I've written. For x5 line, there is a backward path. Similarly, for here also, x1, x5, there are backward paths. You see, you can denote the backward path. So there, I think your concept become clear. For here also, for x2 and x6, there are no backward paths. There are only forward paths. But for x3 and x7, there are backward paths. You can notice it. There are backward paths. Okay. So 0 and 2. W80, W82, W80, W82. Now for stage 3 part, you see, for stage 3, in this first 4 steps, x0, x4, x1, x5, there are no backward paths. So no total factor has been multiplied. But the last 4, W80, W81, W82, W83. Clear? There are 4 backward paths going back upwards. So that's why W8, the total factor is multiplied. Clear? So this is where the butterfly diagram for n equal to 8. Clear? Okay. So likewise, we have done butterfly for n equal to 8. In the next class, I'll be explaining a problem using decimation in time, and I will be showing you the bit reversal process and the comparison between the DFT and FFT algorithm. Okay. Okay.